Hey guys, welcome back to another Minecraft.
Okay, so welcome back everyone. So in today's video we're going to work on some conservation of momentum. So first what I would like to start off with is briefly describing Newton's second law. So recall that Newton's second law is just that our force vector is equal to our mass times acceleration. And our force vector and our mass and our acceleration are both vectors in terms of time. So they change with respect to time. And from this, you can actually see that, well, you can from this you can derive, it's a pretty basic derivation, but you can derive that our momentum vector is equal to mass times our velocity vector. And thus, we note that, well, this part is actually just the derivative of our force vector. So essentially, this is basically, yeah, this is the derivative of our force vector. Or sorry, this is the integral of our force vector, and thus, basically, if we take the derivative of ma, note that we can write a, well, a is by definition our position function, the second derivative of our position function, and this is nothing but, well, we'll let the components be x1, so x1, and then we'll have, I'll write I hat plus x2 j hat plus x3 k hat. And the reason we're not taking derivative of the unit vectors is because they're, whenever we do the product rule on the derivative of a vector, those will turn out to be 0 since they're not dependent on time. So that's why if we differentiate m, the velocity here, so m times the velocity vector v, we'll get our force vector. So basically, we get that the interesting result that the derivative of our momentum vector is equal to our force vector. So that will be useful. And now Newton's third law, which is the fact that the force on one as a result of two, or due to two, so this is a two-particle system, is equal to, we're going to deal with point particles in this case, is equal to the negative of the force on 2 as a result of 1. So this will also be useful in our conservation of momentum video. So let's get started on the real stuff, okay? So consider these 2 point particles. Okay, let's just call this, I guess, particle 1 and particle 2. And we'll usually denote these as alpha equals 1 and alpha equals 2. Okay? And they exert some kind of force on each other, so we can write it as such. So this will be some kind of force, the force on 2 due to 1. Actually, this will be, my bad, this is the force on 1 due to 2. We'll have this magnitude. And this is the force on 2 due to 1. Okay. And we also consider that there are some kind of external forces acting on these guys. So we'll denote the external force on 1 as F sub 1 ext, and here we'll denote it as F sub 2 ext. So now let's consider the total force in this two-particle system. Well, our first force, our F1, the force on our first particle is just going to be the force on 1 due to 2 plus the external forces on 1. And the total forces on 2, particle 2, is just going to be the forces on 2 due to 1 plus yada yada yada, the external forces on 2. Okay, now the total force is trivially F, we'll denote it as F, equals F on 1 due to 2 plus F on 2 due to 1 plus our external forces F sub 1 ext plus F sub 2 ext. Okay, and note that and again we're dealing with classical mechanics here, so let's just assume this is an inertial reference frame. So Newton's law holds that, well, these two will cancel out since F of 1 on 2, the forces of 1 due to 2 is equal to negative forces on 2 due to 1. So these will cancel out to 0. And we're just left with these two external forces. And also what we showed here is that, well, the total force is equal to the time derivative of the total momentum. So this is equal to this. Okay, so this is an interesting result. And to look at a special case of this, which will show us conservation of momentum for a two-particle system, if the total number of external forces is 0, then the amount of momentum that goes into our system is constant. So that is the conservation of momentum for a two-body system. And now we'll generalize this to an n-body system. So let us just erase this. We'll keep these crucial ideas up here. Okay, now let's finish this up. So consider our particles alpha equals 1, 2, 3, 4, all the way to n, capital N. So there are n different particles in our system here. And to calculate basically the force on a given particle alpha, so the force on a given particle alpha is equal to the sum over all beta not equal to alpha. So beta not equal to alpha. And times force on alpha due to beta. So this is summing over all the possible beta values. And we define beta to be, so given an alpha, beta can be any of these other two integers here. So, well, yeah, this can also be beta, essentially. So this is our notation with summation. This is our summation notation. But we can't forget the external forces on A, so we simply just add on the external forces. So we'll just denote that, like last time, as F sub alpha ext. Okay, now we want to sum over all our particles in the system. So now we just sum both sides of this. So we just sum over that for all, we'll just sum over all possible alpha here. So we get that basically alpha, or you could write from, let's say, n equals 1 to capital N. So summing over all alpha, we get that this is just going to be, we can use the distributive property of summation notation. So alpha beta not equal to alpha of f of, oops, I wrote A instead of alpha, f of alpha beta plus summation alpha f of alpha ext. Okay. Okay, so now let's focus on this part. Okay, so note that we can actually pair things up in this case. So essentially what we can do here is, what we're going to have here is basically we're going to sum over all of the beta values here, and then we're going to sum over all of the alpha values. So essentially we're going to be able to pair up, for example, f sub basically F the force on 1 and 2, and we're also, for example, going to be pairing up. So we're going to have some stuff here and some other stuff here. So this, for example. Okay. So we're going to pair these things up, and note that, well, these things will cancel, right? So let's apply this idea. So we focus on this. So we get that this part is nothing but summation of beta greater than alpha, and we can pair things up, like I said. So we'll have F sub alpha beta plus F sub beta alpha. Okay, and, well, this is 0 by Newton's third law. So this is just going to be 0. So this just goes away, which is really nice. And we're left with this. So, and note that while we're summing over all our forces here, that's just equal to the total momentum in the system. So, thus, the total momentum, the change in momentum, the time derivative of momentum, is just going to be equal to the summation over all the external forces as we suspected, as we found with the two-body particle system. Alpha external. And again, here, if our total external forces is 0, then the change in the momentum in our n-body system is 0, and thus this is the conservation of momentum. So that is about it for this video, and hopefully enjoyed. Goodbye.